Water leaking onto a floor forms a circular pool. The radius of the pool increases at a rate of 4 centimeters per minute. How fast is the area of the pool increasing when the radius is 5 centimeters? So we have water leaking onto a floor and there is a circular pool. So we have a circle. I want to label my circle with a radius of r. Now notice that I'm not labeling the radius with an actual number because the radius is increasing. If something is changing as time goes on, you are not allowed to mark it with a number. You have to mark it with a variable, okay? It says the radius of the pool increases at a rate of 4 centimeters per minute. So if r is the radius, then that means dr dt, the rate of change with respect to time, increases, so that means it is a positive 4 centimeters per minute. So remember, step 1, draw a picture, make sure it's labeled with appropriate variables. Step 2, write out what you know. I know that the rate of change of the radius with respect to time is a positive, pay attention to your positives and negatives, 4 centimeters per minute. How fast is the area increasing when the radius is 5? So our question is, what is dA dt? What is the rate of change of the area with respect to time when r is equal to 5? So this is when r is equal to 5. Radius is not equal to 5 the whole time, but at this point in time, what is the area, the rate at which the area is changing? And you know you're looking for a rate because it says how fast is the area increasing. It doesn't say what is the area, it says how fast. So what is the rate? How fast is a question about rate. So how fast is the area changing? All right, so once you have your basic information, we're going to go ahead and write an equation. So what's the equation of area with respect to the radius? Area is pi r squared. Once you have your equation, again, we can't plug in numbers if the variables are changing. Is the area changing as time goes on? Yes. Is the radius changing as time goes on? Yes. So I'm not allowed to plug in numbers yet. Then I'm going to find the derivative with respect to time. The derivative of area with respect to time is dA dt. On this side, I can use the power rule, 2 pi r, and then the chain rule, the derivative of r with respect to t, dr dt. Now that I've found my related rate problem, now I can plug in what I know. I do not know dA dt, that's my question, but I do know that we're looking for when the radius is 5, and I know that dr dt is 4. Okay. And if you wanted to, you could even, just for fun, you could plug in 5 centimeters and 4 centimeters per minute. And that would give you 2040 pi centimeters squared per minute, which makes sense because dA dt, the rate of change of area would be centimeters squared, and then t is in minutes. So please make sure that your units align. Yeah. Let's continue our 712 related rates notes. So we're going to do 3 examples. Our first example, a conical paper cup is 10 centimeters tall with a radius of 10 centimeters. The cup is being filled with water, so the water level rises at a rate of 2 centimeters per second. At what rate is water being poured into the cup when the water level is 8 centimeters? So first step, draw a picture. I have a conical paper cup, not paper cut, a conical paper cup. So a cone looks like this. I am going to need to label some stuff. So the cup is being filled with water. So that doesn't mean it's always filled with water. That means it's being filled with water. So as I fill up the cup, it's not going to be at the very top. It's going to be like somewhere in between. So this is going to be a very common thing with related rates is like tanks being filled or tanks being emptied. So just keep in mind that the entire thing is not full the entire time. And your water level might be increasing or decreasing. So this is actually the radius and the height that I'll be looking at, or the depth. I'm looking at the radius and height of the water, not the actual cup. Now it tells me that the entire cup is 10 centimeters tall. So I can label that. So I'm out of space here. I am allowed to label my height of the entire cup as 10 because the entire cup is not changing height. Just the water level is changing. And the radius of the entire cup is 10. And again, that's not changing because the cup itself is not changing. It's only the water that is changing. Now, the nice thing about cones is that it gives us similar triangles. So the radius and height of the water level is going to be proportional to the radius and height of the entire thing. We'll deal with that here in a second, but I want to go through the rest of the problem and write down what I know. The cup is filled with water, so that the water level, oh my gosh, I can't talk, rises at a rate of 2 centimeters per second. So the water level is rising, so dH dt is positive 2 centimeters per second. At what rate is the water being poured into the cup? So how much water is what we're talking about? The amount of water, the rate of change of the amount of water being poured into the cup. Now, the total amount of water being poured into a cup, that relates to the volume. So dV dt is my question here. What is the rate of change of the volume when the height is equal to 8 centimeters, when the water level is 8 centimeters? So what I want to do here is write an equation so that I am relating my height and my volume. And then I will take the derivative to relate dH dt to dV dt and go from there. So as I was saying earlier, the nice thing about cones is that it creates similar triangles. So the radius of the entire cup is 10. The height of the entire cup is 10. That is proportional to the radius of the water level versus the height of the water level. Okay, so you can set up a basic proportion here, and you get a 1-to-1 proportion. So the radius is equal to the height. So if your cup is halfway up the height, I'm sorry, if the water level is halfway up the height of the cup, the radius would be 5 and the height would be 5, et cetera, et cetera. The radius is going to be equal to the height because that proportion is going to hold. So this is, again, a very common thing that happens when you have a cone, is that you can use similar triangles and set up a proportion. So if the radius is equal to the height, and I need to set up an equation that relates volume and height. So I know the volume of a cone is 1/3 pi r squared h. I'm going to write this all in terms of h since I know what dH dt is, and I'm looking at when my height is 8. So in order to rewrite this so that it's just a bunch of h's, well, since r is equal to h, that's 1/3 pi h squared times h, which is 1/3 pi h cubed. So I can rewrite my volume just in terms of h, and then I can take the derivative with respect to time. The derivative of volume with respect to time is dV dt. The derivative of 1/3 pi h cubed, so again, the 1/3 is a constant. The pi is a constant, so they just kind of stick around. The derivative of h cubed is 3h squared times dH dt. Don't forget to take the derivative of the inside variable. Any variable that you start out with before you take the derivative, make sure that it has its derivative with respect to time in the resulting in the result. So we have v, derivative is dV dt. We have h, the derivative is dH dt. Okay, then I can plug in what I know. I'm looking for dV dt because remember we're looking for the rate at which the water is being poured into the cup. And we know that h is 8. So it's going to be, I can cancel these 3's here, pi times 8 squared. And the water level is changing at a rate of 2 centimeters per second. So I get dV dt is equal to 64 times 2 is 128 pi. And then volume would be in centimeters cubed per second, because that's my time. So water is being poured in at a rate of 128 pi centimeters cubed per second. That's how quickly the rate of change of volume, that's how quickly the volume is changing. For this next problem, we have a 20-foot ladder. It's sliding down a vertical wall. So we have a wall, we have a ladder, and it's sliding down at a constant rate of 2 feet per second. So I've got, I'll call this Y, that's the height of the ladder. As it falls, the base must be going down. Like the ladder can't be, it's not like it can be the same length away because then the ladder would be shrinking. The ladder is not shrinking. So the base is also going to be moving. So I'm going to go ahead and let that be X. So Y is how far up the ladder is on the wall. X is the base of the ladder, the distance it is away from the wall. It says that it's a 20-foot ladder. Now, a ladder can't change lengths, as just because it's falling doesn't mean the length of the ladder is changing. So I am allowed to label this as 20 because that is an unchanging variable here. So again, if something is changing, you have to label it with a variable. If it's not changing, you can label it with a number. It says it's sliding down at a rate of 2 feet per second. So sliding down means the distance is decreasing. So dy dt is negative 2 feet per second. So again, keep in mind your positives and negatives because it will make your entire answer wrong if you have a negative or a positive where it shouldn't be. Y is decreasing by 2 feet per second because the ladder is going down the wall. All right, and then it says for part A, actually I'll do it right here. When the top of the ladder is 12 feet from the ground, so when y is equal to 12, how fast is the bottom of the ladder moving away from the wall? So the bottom of the ladder, that's x. So dx dt is my question. Because it says when the top of the ladder is 12 feet from the ground, how fast is the bottom of the ladder moving away? And remember, x is the length at which the base of the ladder is away from the wall. So I need to come up with some sort of relationship between the variables I see. And so that's going to be x squared plus y squared is equal to 20 squared. And then I'm going to go ahead and take the derivative with respect to time. So derivative of x squared is 2x times dx dt. The derivative of y squared is 2y times dy dt. Use the chain rule. And the derivative of 400 is 0. All right, now we are solving for dx dt, but we do know what y is. We do know what dy dt is. Oh, but we need to figure out what x is. So before we can solve for dx dt, I'm going to have to solve for x. So the way that I can solve for x is plug x into my original function. Plug y into my original function to solve for x. So 12 squared equals 20 squared. This is a special right, not a special right triangle. This is a Pythagorean triple. So this is 4 times 5 squared. This is 3 times 4 squared. So this is going to be 4 times 4. So I know x is going to be 16. If you don't believe me, you can actually do x squared equals 400 minus 44. So x squared is equal to 256. So x is equal to 16. Okay, so sorry, it's probably getting cut off here. So anyway, we are using the original function. We can solve for x. We get x is equal to 16. Now I can plug that back in. 2 times 16 times dx dt plus 2 times 12 times negative 2 is equal to 0. So 32 times dx dt is equal to, so this becomes negative 48. If I add that to the other side, I get positive 48. So I get dx dt is equal to 48 over 32, that's 6 over 4, so that's 3 over 2. So 3 over 2, and we are in feet per second. dx dt is 3 over 2 feet per second. So that makes sense that it's a positive number because remember, as y is going down, x must be increasing. Okay, just think about like the way that the ladder falls. Okay, it's going to be like over here. So x is going to increase as the ladder falls. All right, for part B, it says, at what rate is the angle theta between the ladder and the ground? So theta is between the ladder and the ground. How is that changing when the top of the ladder is 12 feet from the ground? So now I'm looking for d theta dt. So that is an angle measure. We will always be using radians in this class. Just to remind you, the derivative of sine is cosine if you are doing radians. The derivative of cosine is negative sine if you are in radians. So we will only be using radians. Do not just try to convert to, degrees. All right, so d theta dt is what we're trying to find. So I'm going to use sine, cosine, or theta. It's up to you what you want to use. I'm going to use sine because I know in SOHCAHTOA I get opposite over hypotenuse. Again, 20 I am allowed to plug in because 20 is not changing. Y is changing, so you cannot plug in 12 before you take the derivative. So then I take the derivative of both sides. The derivative of sine is cosine theta times d theta dt. Don't forget your chain rule. You have to take the derivative of the inside, which is d theta dt. And then the derivative of 1/20th over y is 1/20th dy dt. Okay, so then, I know I'm looking for d theta dt. I know what dy dt is. It's still -2. But what's cosine theta? So to solve for cosine theta, CAHTOA, cosine is adjacent, which we know from doing the previous problem is 16 over 20. So cosine over 20 is 4/5. And then I can plug that in. I get 4/5 times d theta dt is equal to 1 over 20 times -2. Multiply both sides by 5/4. And I get -1 over 8. And we are in radians per second. So again, you're going to be in radians when you are solving for theta. And notice that I did not actually solve for what theta equals. All I did was I used I needed to find what cosine of theta was. So I used SOHCAHTOA to figure that out. Okay, and then lastly, part C. At what rate is the area of the triangle changing when the top of the ladder is 12 feet from the ground? So area, dA dt, the rate at which the area is changing is my question here. So let's set it up. Area equals 1/2 base times height. So dA dt is equal to, all right, and I am going to have to use the product rule here. So f prime times g plus g prime. Oh, I did that totally wrong. The derivative of 1/2 x is 1/2 dx dt. The derivative of x is dx dt. So f prime g plus g prime. The derivative of y is dy dt times f 1/2 x. So you do have to use the product rule. dA dt is what we're trying to find. And since in all of these instances, it's when the ladder is 12 feet from the ground, I can go ahead and just use my previous information. So dx dt was 3/2, y is 12, dy dt was -2, and x was 16. So dA dt is equal to 36 over 4 is 9. Minus 16. So we get dA dt is equal to -7. And we are in feet squared per second. You are not allowed to forget the units ever. So please make sure that you are using the correct units in context of the question being asked. Area is going to be feet squared. Volume would be feet cubed. If it was just the length, that would just be feet. And then look at your time. This is going to be in seconds, I should say. Okay, so for this next problem, Ron Weasley is traveling west at 50 miles per hour. Harry Potter is traveling north at 60 miles per hour. Both are heading for a... So let's draw a picture. Ron Weasley is traveling west. Harry Potter is traveling north towards a common intersection. So west. So I'm going to put an arrow here, but really it's a length. And then same thing here. And I'm going to label this R, and this is H. So R represents Ron's distance. H represents Harry's distance. They're heading towards a common intersection. At what rate are they approaching each other? So at this moment in time, Harry might be here, Ron might be here. I want to know what's the rate at which they are approaching each other. So I'm going to need the distance they are from each other, which I'm going to call like X. I don't know, it doesn't matter. So Ron is traveling west at 50 miles per hour. So dr dt is equal to, now the miles is my distance here, right? He's traveling at 50 miles per hour. Is that distance increasing or is that distance decreasing? Well, if Ron is traveling towards a common intersection, he's not heading away from it, his distance is decreasing. As time goes on, he is getting closer and closer to that point of intersection. So dr dt is negative 50 miles per hour. Same thing with Harry. Harry is getting closer and closer to that point of intersection. That's going to be a negative rate because his distance is decreasing. And then we're trying to figure out at what rate are they approaching each other, their distance from each other. How is that changing? So that's my dx dt. That's my question. At what rate are they approaching each other when Harry is 0.3 miles away and Ron is 0.4 miles away from the point of intersection? Okay, so we need a basic equation to relate all of these things, R, H, and X. Ron is traveling west, Harry is traveling north. That creates a 90-degree angle, so you should be able to see pretty quickly here. Or go back to the previous page. Remember, we have all those like geometric relationships that you might want to try, like SOHCAHTOA, Pythagorean theorem in this case, area formulas, all that. So in this case, I would use the Pythagorean theorem to relate these three sides to each other. H squared plus R squared is equal to X squared. And you don't want to plug in any numbers because everything is changing. Ron is heading towards the intersection. Harry's heading towards the intersection, which means they're also getting closer to one another. So you can't plug in what X, R, or H are yet. You need to take the derivative with respect to time. So the derivative of H squared would be 2H times the derivative of H, which is dH dt. The derivative of R squared is 2R times the derivative of R, which is dr dt. And the derivative of X squared is 2X times the derivative of X, which is dx dt. And then once you have your derivative, now we can start plugging in what we know. So we know that I'm going to go ahead and divide everything by 2, actually, just to make my life a little bit easier. If I divide everything by 2, the 2's go away. Okay, H is 0.3. dH dt is negative 60. R is 0.4. dr dt is negative 50. And then X, I don't know, and dx dt is also unknown. That's what we're trying to find. Okay, so this gives me a little bit of an issue because I have 2 unknowns, right? So let's see, dx dt is my final result. That's what I'm trying to figure out. So is there a way for me to solve for X? Well, look at your original problem. We know what H is at this moment in time. We know what R is at this moment in time. Can we figure out what X is at this moment in time? Yes, we can by using the original equation. So 0.3 squared plus 0.4 squared is equal to X squared. This is a 3, 4, 5 triangle, so X is equal to 0.5. If you don't believe me, use a calculator and double check. So at this moment in time, they are 0.5 miles away from each other. So then I can plug that back into my derivative. So 0.3 times negative 60. I don't know why I'm struggling with this right now. Negative 180 divided by 10 is negative 18. Plus 0.4 times negative 50. So that's negative 200 divided by 10, so negative 20 is equal to 0.5 times dx dt. So that's negative 38 is equal to 1/2 times dx dt. Multiply both sides by 2, I get negative 72 equals dx dt. So let me go ahead and make sure I have this with the correct units. Dx dt is negative 72. So x is in miles and time is in hours. So they are getting closer to one another at 72 miles per hour. So that's why my result is negative, because that distance of x, that distance is going to be decreasing. So the rate of change would be a negative value. Okay. All right, for this next one, Miss Bisagno is 12 feet away from the boat and holding onto a rope for dear life. One of her students is on the deck of the ship and is pulling in a rope at 0.5 feet per minute. What is the rate of change in the angle formed from Miss Bisagno to the bottom of the boat? So we've got a lot here going on, but we are going to go ahead and draw a picture first so that we have an idea of how these things relate to one another. So we've got a boat. I'm just gonna kind of draw like this is the boat. It's not great. Okay, there's a boat. Here's Miss Bisagno. She is like holding on to a rope for dear life. One of her students is on a deck of a boat. So here's my student over here. They're holding on to a rope. I'm gonna assume that rope is really tight. And I'm in the water holding on. Okay, now at this moment in time, I am 12 feet away from the boat. But the student is pulling in the rope. So as the rope gets shorter, I'm being pulled closer to the edge of the boat. That means that this distance, I'll call this x, that distance x is changing as I get closer and closer. The deck of the ship is 16 feet high. Now that is not changing, so I am allowed to mark that as 16 because the boat, we have to assume, is going to stay at 16 feet. And then we know that the rope is being pulled in at 0.5 feet per minute. So that, I'll call that Z, I guess. So Z is changing because the rope is being pulled in. And we are finding the rate of change in the angle formed from Miss Bisagno to the bottom of the boat. So we are looking at a rate of change of an angle here. So I need to also label my angle. And I'm going to go ahead and label that theta. So we know that the rope is being pulled in. So dz dt is negative 0.5 feet per minute. And that is negative because the distance is decreasing. The rope is not being let out. The rope is being pulled in. So that distance is decreasing. So it's a negative rate. And we are looking for what is the rate of change of the angle. So d theta dt is what I'm questioning, or is what I'm trying to figure out. So first thing I need to figure out is what is a, oh, I'm sorry, I should have put when. X is equal to 12, because at this moment in time, I know I am 12 feet away from the base of the boat. Okay, so I need to set up a basic equation. So in order to relate theta to x and z, or if I want to relate theta to 16 and z, I actually have a few different options, because with SOHCAHTOA, I can use sine, I can use cosine, I can use tangent. You can actually do whatever you want. You can use sine, you can use cosine, you can do tangent. I'm going to go ahead and use sine. And that's because I know dz dt. So I definitely want to use my z. So that gives me either I want to use cosine or I want to use sine. Because I'm given dz dt. So I definitely want to have a z in there. And I kind of want to use the 16 because that's not changing. The derivative of 16 will just be 0, so that kind of makes things easier for me. So I'm going to go ahead and use sine. So sine of theta, SOHCAHTOA, so sine is opposite over hypotenuse. And then when I take the derivative of sine theta is cosine theta times, don't forget to take the derivative of the variable with respect to time, d theta dt. And the derivative of 16, that's 16z to the negative 1, right? So that's negative 16z to the negative 2 times dz dt. We have to take the derivative with respect to time. So that's why I wanted to use sine, was because it just gave me 16 as a constant. If I had used cosine, that would have been x over z. I would have had to use the quotient rule, because that would have been two variables. And the derivative of a variable divided by a variable, you have to use a quotient rule, the quotient rule there. So with this, I didn't have to use the quotient rule. And then let's plug in what we know. Cosine theta, I don't know right this minute, so I'm going to hold off on that. I obviously don't know what d theta dt is. That's what I'm trying to solve. I know that, let's see, do I know what z is? I do not know what z is right this second, but I can figure that out. And dz dt is negative 0.5. Okay, so I have a few unknowns. Cosine is an unknown, and z is also an unknown. So let's look at things we can do to solve. So I know this moment in time is when x is equal to 12. So that gives me, again, at this moment in time, 12, 16. I can figure out what z is by using the Pythagorean theorem. So 16 squared plus 12 squared is equal to z squared. Is this a 3, 4, 5? 16 is 4 times 4. 12 is 4 times 3. It is a 3, 4, 5. So z is 4 times 5, which is 20. So z is equal to 20 feet. And then cosine, so SOHCAHTOA, cosine is adjacent over hypotenuse. So at this moment in time, the adjacent side is 12, and the hypotenuse is 20. So at this moment in time, I can figure out what cosine is, which is 3 over 5. So I can figure out both of these by using Pythagorean theorem and SOHCAHTOA, and then I can go back and plug them in. So cosine was 3/5 d theta dt. Notice that I didn't have to find what theta is. I just had to find what cosine of theta is using SOHCAHTOA. So don't overcomplicate things, especially because you're not given a calculator for a lot of these problems. I haven't used a calculator once. Don't overcomplicate it, just use SOHCAHTOA a lot for these angle type of problems. Z was 20 squared times negative 1/2. So that is 3/5 times d theta dt, which is, let's see, that's 8. That's going to be a positive, so 8 over 20 times 20. Again, I'm not using a calculator, so times 5/3 theta dt is equal to 8 times 5 is 40. 40 divided by 20 is 2. 2 over 20 is 1/10. So I get 1/10 times 1/3, which is 1 over 30. Now, d theta dt is going to be the units of an angle over, in this case, minutes, right? Okay, so what are my units? Are they radians or degrees? So, as I've said since the first day of school, you are never, ever, ever in degrees in this class unless we're talking about temperature. So d theta dt is equal to 1 over 30 radians per minute. Fun fact, I don't know if we've talked about this. The derivative of sine is cosine if you are in radians. If you are in degrees, the derivative of sine is not cosine. If you are in degrees, your derivatives for trig that you know do not work. So you have to be in radians mode, which means you have to think about things in terms of radians, which means your answer for a rate of change of an angle will be in radians, because you are not finding the derivative in degrees. You are finding the derivative in radians. So the angle is changing at a rate of 1 over 30 radians per minute.